Hello and welcome to the chapter on special relativity. So a couple chapters ago, we went over general relativity, which is actually the more complicated uh, form of this. And this is an especially complicated or thought-provoking section of physics that you usually don't get into until after you've been going through physics for a while. But we've talked about it passingly in the first chapter and in chapter 7. We talked about general relativity. So it is with this in mind that we go forward into special relativity. So because the book is aimed at people who know algebra, but isn't aimed at especially difficult calculus or math or anything above algebra. A lot of what ends up happening for this chapter is thought experiments or Gedanken experiments, as the Germans say, uh, which allow us to see the changes and the effects of a couple of postulates that Einstein made in 1905 that really gave rise to this ideal. So, classical relativity was developed by Galileo and Newton and describes how velocity and position look different depending on the reference frame you're moving in. So, one thing uh, that classical relativity explains, as you'll remember, is that if you're going at a highway or down the highway at 60 miles per hour, it's going to look to you like a tree that's on the side of the highway is coming towards you at 60 miles per hour. So there's a difference in what you're looking at based on what you decide to choose as your reference frame. So the reference frame is basically just if you choose the car to be stationary and everything in the world is moving around it, or if you choose the world to be stationary and the car is moving relative to your spot on the side of the road. So that's classical relativity, and Einstein developed special and general relativity. I think special relativity was developed in 1905 and general relativity in 1918, but both of them uh, describe how space and time warp as in special relativity as you go near the speed of light, and in general relativity as you go into high gravity situations or are accelerating. So the postulates of special relativity are that the laws of physics are the same in all inertial frames. So whether or not you're going constantly at the speed of a car or whether you're sitting on the side of the road, both of those are going to have the same physics and the same, uh, or they're going to have the same physics, and you'll see the same results when you look at momentum or energy or acceleration or anything like that. But an inertial reference frame means that it's a constant velocity, so it's not an accelerating reference frame. And then the second postulate of special relativity is something that didn't come to light until the 20th century or the very late 19th century. It's that the speed of light is the same in all inertial reference frames and is not affected by the speed of its source. So what you have here on the right-hand side is a bit of the Michelson-Morley interferometer that want to prove that this is true. And what basically uh, happened, what the importance of this sentence is is that up until the late 19th century, up until we have this experiment, we thought that everything was moving in something called the ether, which was a position, which was the privileged position where everything was at a constant velocity, or where everything was not at a constant velocity, but moving at some velocity relative to the ether, which was stationary, and the speed of light was relative to the ether. So if you were going 300 meters per second in the opposite direction of the if something was stationary in the ether, then it would be going at a velocity of 3 times 10 to the 8th meters per second. And if you were going 300 meters per second, then that would mean uh, either uh, towards a light source, uh, then that would mean that the speed of light would be slightly slower, or slightly faster, or if you were going away from the light source, it would mean that the speed of light was going slightly slower as it had to catch up with the extra distance that you were traveling. But what ended up happening instead is that we found that the speed of light is constant no matter how fast you are going in an inertial reference frame. So, uh, what this also means is that uh, if somebody is going at 3 meters, running at 3 meters per second, and throws a ball at 10 meters per second, then from to somebody who's stationary on a football field, it would look like the ball was going at 13 meters per second, because it adds on top of the 3 meters per second that the person was already going. But if you emit light and you flash a bulb of light and it goes 3 times 10 to the 8th meters per second forward from your perspective as you're running at 3 meters per second, it would also go at exactly 3 times 10 to the 8th meters per second, looking from the side of the field. So it doesn't matter what position you're in. It doesn't matter what velocity you're going in at relative to another reference frame. It's always going to be the same speed of light no matter what, which is really, really mind-bending if you think about it. And then the speed of light is given by the constant c, which is 3 times 10 to the 8th meters per second, or more precisely, is defined to be exactly 299,792,458 meters per second. But to within about 1% or half a percent, you can approximate that as 3 times 10 to the 8th meters per second. So the first weird thing that happens because of this, the first weird thought experiment that the book brings up that happens because of this, is that if two lights are flashed simultaneously, uh, if somebody is sitting in the middle of a car and two lights are flashed simultaneously, a car that's moving at a velocity to the right, and two lights are flashed simultaneously from the viewpoint of observer B, then that would mean that the light that travels from the right flash is going to reach the observer A, who is the person in the middle of the card that's moving before the left flash, because you're moving towards that light, uh, the light is going to hit you, or the light is going to hit observer A first, on the right and then the left, because it's moving towards the right side and away from the left side. But for observer A, uh, it looks, because the lights are exactly the same distance apart, it looks like the lights flashed at different times, which means that given a certain reference frame, looking at a certain, whether you're the observer on the car or you're the observer on the side of the train, these two events of the lights flashing no longer occur at the same time, which is just a thought experiment and a ideal that comes out of this ideal that light has to travel the same at any given uh or at any given velocity, any given reference frame. And then the other consequences of special relativity, which is SR, that I want to talk about, is that because the speed of light is constant in any reference frame, and is given by a change in distance over time. So if the speed of light is a change in distance over time, uh, which is the definition of a velocity, it's the definition of a speed. And that means that distance and time have to warp depending on your reference frame in order to accommodate this. So because the distance traveled over a certain amount of time is constant, then but it looks different from different reference frames, because the distance traveled over a certain amount of time is constant, but uh, the properties, the simultaneity, and the general properties of space and time, of the mathematics behind it, uh, have to accommodate this. That means that distance and time, which is how far the light travels over a given time, have to warp depending on how fast you're going. So time dilation is the phenomenon of time passing more slowly for an observer who is moving relative to another observer. So for example, we have in sci-fi novels and movies such as Interstellar or Ender's Game, you have observers going near the speed of light, and as they go closer to the speed of light, or they pass through a heavy gravitational field, it makes it so that their experience of time is much shorter than the experience of time of somebody going who's not going as fast, who's stationary in the other reference frame. So if you go on a spaceship to Earth, from Earth to the end of the solar system and back, then you're going to have the twin paradox, where if one twin is stayed on Earth and the other twin goes in the spaceship and to the end of the solar system and back, then the twin who went on the spaceship is going to appear significantly shorter, younger than the twin who stayed at home. And then the shortening of distance experienced by an observer moving with respect to the points whose distance apart is measured is called length contraction, is another thing that comes up in special relativity, where uh, something that has a proper length. So if you have a meter stick or a pole and you're running really fast with it, then to an outside observer, it would look like the meter stick is shorter than a meter to somebody who's just standing on the earth while you're going at 3/5 of the speed of light or whatever. And all of these become more apparent, become more prevalent when you talk about higher speeds. So the closer you're getting to the speed of light, the more apparent these values are going to be, or these distortions are going to be. And then I think the last thing to bring up is the relativistic momentum and the relativistic energy, where P, the momentum, is given by gamma m times the velocity, where gamma is just a value that goes up with higher speeds, and u is the velocity seen by a stationary observer. So it's just the momentum that we got earlier times some value that goes up to infinity the closer you get to the speed of light. So momentum goes up to infinity the closer you get to the speed of light. And then you also have the most famous equation in physics, E equals gamma mc squared, or E equals mc squared if you decide to treat m as something that changes, or mass as something that changes with velocity, which is a certain way to look at it. Not everybody does look at it that way, but you can say that mass goes up with a higher velocity and E equals mc squared, or you can say E total is equal to gamma mc squared, where gamma again goes to zero, infinity as u as the velocity of the object nears the speed of light. So as the velocity of the object nears the speed of light, energy goes to infinity, which means that you cannot go any faster to the speed of light, because the closer you get to the speed of light, the more energy it would take, and there is a finite amount of energy in the universe. This is where we get the fact that in addition to being constant, the speed of light is the highest speed that you can go in the universe. And then that's going to be it for my presentation. I hope that that made sense. In the book, this does actually go over a lot of thought experiments rather than just going through the algebra of something. So it does explain where it comes from without having to deal with algebra as much as you do in other chapters. And then in addition, I am always available to talk to you about any of this or any questions that you might have. Thank you very much, and I'll see you next lecture.